This is the town of Malaga in Washington. It's a small town of about 4,500 people that sits quietly on the Columbia River. But something is happening in this town that could transform not just the town, but the entire world. And if this town succeeds at what they're doing, it will change the trajectory of civilization more than artificial intelligence, more than quantum computing, and more than anything else on the technological horizon today. You know, when humans first harnessed fire about 1.5 million years ago, the importance of fire was not just warmth. Fire was calories on demand, cooked food that released more energy with less chewing, and protection from predators. Anthropologist Richard Wrangham has even argued that fire and cooking may have been what allowed human brains to grow larger, giving us the energy surplus to think abstractly. Fast forward to 3000 BC, fire's ability to smelt copper and tin into bronze created the Bronze Age. Empires started rising, monuments started getting built, and history began showing a pattern. Those who control the energy control the future. Eventually, humans learned to harness wind and water, and those humans that did created civilizations, like the Phoenician traders, Greek city-states, the Vikings, and later, the European colonial empires. They all depended on harnessing the power of the wind and the sea to dominate trade and exploration. By the 1700s, coal and steam turned Britain from a damp island into the most powerful empire the world has ever seen. In 1712, Thomas Newcomen built the first practical steam engine to pump water from mines. By 1769, James Watt's improvements made steam engines efficient enough to power factories, trains, and ships. And the growth of this industry was staggering. I mean, in 1700, Britain mined about 3 million tons of coal per year. By 1900, it was 225 million tons per year, a 70-fold increase in 200 years. This cheap, dense energy gave Britain the industrial edge to conquer, colonize, and industrialize on a scale that the world had never seen. The next empire ran on oil. In 1859, Edwin Drake drilled the first oil well in good old Pennsylvania. By the 20th century, oil had become the bloodstream of modern life, fueling cars, airplanes, plastics, fertilizers, and pharmaceuticals. And as we know today, whoever controlled the oil had leverage over the world. I mean, Winston Churchill, as the first Lord of Admiralty in 1911, switched the British Navy from coal to oil, even though Britain didn't control really any of the oil reserves. It was risky, but oil's energy density was just unbeatable. Later in World War II, Germany invaded the Soviet Union partly to seize oil fields in the Caucasus. By the 1950s, the United States controlled half of the world's oil production. It gave them power both at home to fuel cars, houses, and factories, but it also gave them power in terms of geopolitical dominance. So fire gave us survival, sails gave us empires, coal gave us industry, and oil gave us modern times. But this has posed the question, what's next? For thousands of years, humanity has looked at the sun and wondered, what's keeping that fireball burning? In ancient mythologies, the sun was a god. Ra in Egypt, Helios in Greece. But it wasn't until 1920 that British astrophysicist Arthur Eddington proposed a revolutionary idea. That stars are not powered by gods or powered by coal or wood or burning some sort of fuel. They're actually powered by fusing atoms together. In simple terms, fusion happens when two atomic nuclei, like hydrogen, smash together with enough force to combine into a heavier nucleus, but also releasing enormous amounts of energy in the process. It's Einstein's equation E equals mc squared in action, or energy equals mass times the speed of light squared. Meaning that when a tiny bit of mass vanishes from this process, what's released is pure energy. And the potential for this energy is insane. Seawater has a tiny bit of the fuel called deuterium that is used to do nuclear fusion. And a single fairly small glass of seawater can produce as much energy as 258 pounds of coal. And nuclear fusion does this with pretty much no emissions, very little pollution, very limited radiation or byproducts, and it might be able to do it without starting wars. So hearing about how much energy could be created and harnessed by countries if they were to get nuclear fusion correct, well, this started a nuclear fusion race, specifically between the Soviet Union, Europe, and the United States. In the 1950s, scientists were trying to build machines that could replicate nuclear fusion, and two main ideas emerged. Magnetic confinement fusion, which is giant donut-shaped machines called tokamaks, invented by Soviet physicists Igor Tamm and Andrei Sakharov. The idea was to use powerful magnetic fields to trap plasma, a superheated gas of ions, at temperatures hotter than the core of the sun. The second idea was inertial confinement fusion, which was using lasers or particle beams to compress tiny fuel pellets until they exploded in a burst of fusion. Over the years, billions of dollars poured into these experiments. Countries built machines the size of cathedrals, but they all hit the same wall. Plasma was a little bit unruly. It wobbles, it leaks, it cools down faster than they can heat it, and no matter what the scientists and physicists did, the plasma always seemed to be the one that got away. By the 1970s, the running joke in physics departments was that fusion power was always 10 years away. That was until 1989, when two chemists named Martin Fleischmann and Stanley Pons claimed they had achieved cold fusion in a simple tabletop experiment. The media exploded after this. The New York Times ran headlines about an energy revolution. Investment was ready to be poured into nuclear fusion companies. But within months, the claim unraveled. Other labs couldn't really replicate this cold fusion experiment. Cold fusion was exposed as either error or fraud, and the entire field of fusion research became pretty radioactive, pun intended. Funding dried up. Physicists who dared talk about fusion were laughed at. For decades, it sat in the scientific wilderness, a dream, a mirage that was always out of reach. However, there were, in some people's minds, still this one thought. 1 kilogram of pure fusion fuel could release as much energy as 10 million kilograms of coal. So even though it seemed unlikely, whatever company or scientist or physicist could figure out how to get fusion right would change the world forever. So some teams and countries kept working away, ever so subtly. And over time, because other technologies got better, fusion got a little bit more reasonable. For example, superconductors got better. In 2018, MIT scientists announced a breakthrough in high-temperature superconducting magnets. Smaller, stronger magnets meant you could trap plasma more effectively, without building reactors the size of football stadiums. Computing also got way better since the 1970s, as we all know. All of a sudden, physicists could run high-powered simulations with plasma turbulence, which was once an unpredictable nightmare. It could finally be modeled, predicted, and controlled. All of a sudden, scientists could run billions of plasma simulations in computers instead of relying on trial and error in giant multi-billion-dollar machines. And then finally in 2022, the National Ignition Facility in California did something that was unthinkable. It created the first fusion reaction that had a net positive energy output, meaning more energy came out of the reaction than was put in. This event sent shockwaves through the scientific community. The dream that scientists have had for over 100 years finally came true. It was for the first time theoretically possible to harness the power of an artificial, man-made sun. Now, despite this experiment's success in 2022, the National Ignition Facility is just an experimental facility. It's a test facility for research with no intentions to scale up and make this a nuclear fusion power plant. But there was another company founded 9 years earlier whose intention was to become the first nuclear fusion power plant, and that company is named Helion. In 2013, it started with a group of plasma physicists led by David Kirtley. And they had a bold pitch. Forget the giant tokamaks that every other country and multinational corporation has been trying. Instead, they were going to build something smaller, cheaper, faster, something you could test, iterate, and scale the way Silicon Valley builds software. They called their design pulsed magnetic confinement, and it looks more like a giant science fiction engine more than a nuclear reactor. And here's how it works. Helion fires plasma down two opposing tubes at incredible speeds. Each plasma stream is compressed and accelerated by magnetic fields until they slam into each other at the center of the machine. At that moment, the plasma reaches temperatures of 100 million degrees Celsius, nearly 7 times hotter than the core of the sun. The hydrogen nuclei fuse, creating helium and releasing energy. And here's the clever part. Instead of heating water to spin turbines, which is the old school nuclear and coal plant method, Helion directly converts that plasma energy into electricity using magnetic fields. Pretty much, they are cutting out the middleman of nuclear reactors. The company has tested 6 prototypes so far, each one hotter and more stable than the last. Their next machine, Polaris, is now under construction in Malaga, Washington. And here's the headline that made the world take notice. It claims it will demonstrate net electricity generation by 2028. Not fusion reactions, not proof of concept, but actual electricity going into the grid. For context, the ITER in France, which is one of the most expensive projects that the country has ever done, won't attempt net energy output until the 2030s sometime, if it ever does. Helion is saying, we're going to do this much quicker and for 1/10 the cost. That's why in May 2023, Microsoft signed a power purchase agreement with Helion to buy electricity from its first fusion power plant, becoming the first Fortune 500 company to bet on fusion as a real power source. So why would Microsoft or anyone else care about this? Well, let's do some math. The main fuel Helion uses is deuterium, which is extracted from seawater. And the ocean contains enough deuterium to power humanity forever, pretty much, meaning that the sun will almost certainly turn into a red giant and fizzle the Earth anyways, long before we run out of fusion power from the oceans. There's also no meltdown risk, so unlike nuclear fission, which does scare a lot of people because of accidents like at Chernobyl, nuclear fusion doesn't have a chain reaction to spiral out of control. If something goes wrong in a fusion reactor, the plasma just fizzles out and then everything stops. And then there's also that nuclear fusion pretty much has very little to no nuclear waste. Nuclear fission plants produce waste that can remain radioactive for tens of thousands of years. Fusion byproducts, well, it's mostly helium, so we can, I guess, inflate a bunch of balloons with it, with several other byproducts that are nowhere near as radioactive or as large as is produced in nuclear fission plants. And also, nuclear fusion doesn't produce any pollution. So let's just say Helion and its nuclear fusion power plant works in the next few years. What does this mean for the world? And more provocatively, could the center of this new age of abundance really start in a small farming town in Washington state with a population of just over 4,000 people? Well, it sounds a little bit crazy, but then again, Silicon Valley was once just orchards and fruit canning warehouses that ended up becoming the capital of the digital age. Los Alamos in New Mexico, which was a tiny desert town, gave birth to the atomic bomb and the nuclear era. History has a way of hiding revolutions in unexpected places. You see, empires rise on cheap, reliable energy, and fusion could just be that next step. And the scale it's really hard to comprehend, but I'll try to put some numbers on it. 1 liter of seawater, processed for its deuterium content, could theoretically power a household for an entire year. And the US consumes about 100 quadrillion BTUs of energy per year. With fusion, that demand could be met with just a few truckloads of fuel. So I'm just trying to say here that this isn't just more efficient, this will change all of civilization if this works. Imagine energy so cheap and abundant that the price of electricity collapses not to cents per kilowatt hour, but to fractions of a cent, essentially seeing your electricity bill potentially drop by 99%. Now, there's also a lot of other ripple effects that could come from this power plant. For example, right now everyone knows that AI and data centers require a lot of power. And one of the big bottlenecks for training new AI models is the limitations of the power grid. But with fusion, power-hungry computation becomes kinda trivial. Data centers could sprawl out without guilt. AI training wouldn't be constrained by electricity bills, but only by human imagination. This would accelerate the pace of technological development beyond anything we've ever seen. Secondly, it would not just make electricity cheaper for you, but it would make everything cheaper. Think about everything that uses electricity. Houses, factories, electric vehicles, computers, offices. Imagine if pretty much every aspect of the supply chain and of your life got a little bit cheaper. That's a very likely possibility. Right now, about 40% of the entire world's pollution and CO2 emissions come from power plants. Right now, the world emits about 37 billion tons of CO2 and pollution per year. About 40% of that comes directly from power plants, meaning this technology alone could cut down CO2 emissions by 40% by itself. There's also already some plans and some ideas about fusion-powered spacecraft. You see, currently we use chemical rockets, which are basically just controlled explosions. They're not very efficient. But if we were able to make fusion-powered spacecraft, well, this could cut the trip to Mars down from 6 months to 6 weeks. So for example, Voyager 1, which is traveling at about 38,000 miles per hour, that is the third fastest man-made object of all time. At its current rate, it will take 40,000 years to get to the nearest star. However, with nuclear fusion and with ideas like Project Longshot, all of a sudden you could get to the nearest star system in potentially 100 years or less. Pretty much one very long human lifetime. There's also the geopolitics. I mean, what happens to oil states if the world no longer runs on oil? Saudi Arabia gets 70% of its government revenue from oil, Russia gets about 45% of its federal budget from oil and gas exports, Venezuela, Nigeria, Iraq all depend on fossil fuel exports for survival. Fusion would strip these countries of leverage, and new energy superpowers that develop nuclear fusion technology, they would emerge. It wouldn't be based off of some fossil fuels they found in the ground. It would be built on who is the smartest and who could build the best fusion power plants. But there's also a stark warning to all this. You see, no energy revolution has ever been smooth, ever. Coal gave us the Industrial Revolution, but it also gave us the Black Lung and colonialism. Oil gave us cars and plastics, but also gave us climate change and endless wars. Fusion, well, it might have its own problems. I mean, what if only a handful of corporations control fusion technology? Instead of an energy abundance for all, it could mean a small portion of corporations or countries have an unprecedented wealth concentration. There's also a chance that nuclear fusion isn't all it's hyped up to be. I mean, we do know for sure that we can get it working, but maybe Helion or some of the other companies stumble along the way, and maybe funding or trust could evaporate. And then there's also the risk of, well, currently fossil fuel industries employ millions of people around the world. A giant economic disruption from fusion could be as destabilizing as the shift from horses to cars, only much bigger and much faster. All of a sudden, the oil-rich states will become humanitarian crises. So fusion could save the world, but it will probably fracture it along the way. And that's where we circle back to Malaga. Right now, it's still a farming town. People are pruning apple orchards, kids are riding school buses, trucks are hauling fruit down Highway 28. But construction is well underway for building a machine that, if it were to work, could be the beginning of a new age. The Fusion Age. And this town could end up being like Menlo Park was in 1879 when Thomas Edison lit up the first practical light bulb. Or it could be like dozens of other failed experiments that never really make it into the history books. Regardless, Malaga will be remembered, not for its orchards, not for its fruit, but for daring to build a star in a box. Thanks for watching.